Welcome to Algebra 2. This is section 5.1, nth roots. All right, so this chapter, we're going to start looking at how exponents tie together with different roots that we could take. So it's important that we go back over some of the properties of exponents that we learned from Algebra 1. So the first one, I'm going to take a second and explain these because they make perfect sense when we think about them. First one says if I have two numbers with the same base raised to different powers and I'm multiplying them together, then that means that I can keep the same base and just add the exponents. So just think like if I had x squared times x to the third, that would equal x squared means x times x cubed means x times x times x. So really I'm multiplying together 5 x's. Well, I can write something times itself 5 times as the fifth power, and 2 plus 3 is 5. So that's how we get that property. The second one says if I have a power raised to another power, then it's like multiplying the exponents together. Let's use our example that we had before. If I have x squared to the third power, well, third power means times itself 3 times. So x squared times x squared times x squared. And what does that really mean? That means x times x times x times x times another x times x. Oh, so really I'm multiplying together 6 x's in that case. I can call that x to the sixth. So that explains our product of powers and our power of a power, those rules very, very clearly. All right, the power of a product, if I have a product of two numbers raised to a power, we've seen that. The power applies to both elements inside, both factors in that product. A negative exponent, this is one that comes up quite a bit in this section actually. If I have something raised to a negative power, it's like the reciprocal with a positive exponent in place. So a to the negative m is equal to 1 over a to the positive m. Zero exponent, we've already seen that quite a bit. Anything to the 0 power is equal to 1. The quotient of powers, this just deals with division undoing multiplication. So let's say that we had x cubed divided by x squared. Again, two numbers with the same base and I'm dividing those numbers. Well, think about what that means. In the numerator, I've got x times x times x, and then in the denominator, I've got x times x. Well, in two cases there, the division will cancel out things that are multiplied together, leaving me 1x in the numerator, or x to the first power, which is x to the 3 minus 2. And then lastly, the power of a quotient. If I have a fraction raised to a power, that means the numerator and denominator both get raised to that power as well. All right, and it just means that, say we had x over y to the second power, that means x over y times x over y. How do we multiply fractions? We go across the top, x times x, and we go across the bottom, y times y. So we can see that that exponent clearly should apply to both numerator and denominator. So those rules make sense. And if we haven't been shown why they make sense, there you have it. And we're going to apply them quite a bit today. They can definitely make work much, much easier. All right, we've already kind of casually discussed this in class, but let a to the 1 over n, now we're talking about exponents that are fractions. And here I'm just going to write this a little bit bigger, a to the m over n equals, we can use our power to a power property to say that that's 1 over n times m for our two exponents, kind of split that up. And then we know that 1 over n is a reciprocal, and that's an exponent though. And again, here's where we casually discuss this in class, that's taking something to the 1/2 power is like taking its square root. Well, that's what's happening here. Now, instead of a square root though, we have some number n, and then that nth root of a is being raised to the m power. Okay, and then lastly, the second line here is just describing that if that fraction as an exponent were negative, that not only would we be converting it into roots this way, but it would also be in the denominator because we would also have that reciprocal action happening as well. The best way I can think to describe it is what's the exponent doing? What are the parts of the exponent doing? The numerator is what's making that a bigger power, and the denominator would be making that a smaller power. And to make things smaller, that's where we're applying the root concept. And to make things bigger, that's where we're applying the exponent concept. So it makes sense that after we've changed this, the n, which was the denominator, becomes the root, and the m, which was our numerator, that becomes a power. The powers make it bigger, the roots make it smaller. It just makes sense mathematically. Right, so how they apply to solving. Now, instead of solving an equation by taking square roots of both sides, we're going to be using higher roots to undo higher powers. So it's just important to recognize the patterns for when we have imaginary solutions and when we will actually get real results. So if we have an even root, so let's just say n is an even integer, that means we have an even root like a square root or a fourth root or something. Then if we have a negative input, we'll get imaginary solutions. We've seen that. That's nothing new. But now we can extend that idea beyond square roots to fourth, sixth, eighth, and beyond, those even-powered roots or even-numbered roots. If a equals 0, well, then any root of 0 is going to be 0, so we will get 0 as our one real root. And if a is greater than 0, we can take an even root of a positive number, and we just need to remember that we could have a plus or minus occurring for any of those even roots. So now it's just a matter of extending our idea of solving by taking square roots to work for higher powers. If we have an odd integer, well, now this is something that's new because we've never seen odd roots before. And I'll just point you to maybe the most simple case. If I have the cubed root of -8, well, think about how we can arrive at -8. I could take -2 times itself 3 times. So if -2 cubed equals -8, I should be able to cubed root both sides and find that the cubed root of -8 is equal to just -2. So it is possible to take the cubed root or any odd root of a negative number. So even if our radicand, what's under the radical sign, is odd or negative, if we have an odd root, we will get a real solution. Same if a is equal to 0, and now if a is greater than or equal to 0, if it's an odd root, we do not concern ourselves with plus or minus. We will get one solution if we have an odd root, no matter what. All right, so now we get to the actual problems themselves. Find the indicated real nth roots of a. So for number 6 here, n, the root is 5, and then a, the radicand, is -1. I want the fifth root of -1. If I were to solve that in a calculator, I would say -1 raised to the 1 divided by 5, the 1/5 power. And we find that that solution is -1. Okay? Because we had an odd root, we are allowed to have a negative underneath. And if we undo all that work, we find that the answer is -1. Number 10, I want the sixth root of -729. Well, now I've got an even root, right, a sixth root with a negative underneath, and the directions say find the indicated real nth roots. Because there's a negative for a radicand under an even radical, or a radical with an even root, there are no real roots. So in this case, there are no real sixth roots of -729. If that were a positive number underneath, then absolutely, we would go through the same work that we did in number 6. We would take that positive 729 to the 1/6 power and come up with our answer. But because it is a negative underneath an even radical, there are no real roots for that. Example 2, evaluate without using a calculator. This means that we should be able to simplify by converting to roots and working our way backwards through that. So 81 to the 3/4 power is like, let's see, the denominator makes it smaller, so that's the fourth root of 81, and then the numerator makes it bigger, that's a power on that root. Okay, the fourth root of 81, well, 81 is 9 times 9. So I can rewrite it that way. And then 9 times 9, each 9 is 3 times 3. Okay, so I've got the fourth root of 3 times itself 4 times. That's the fourth root of 3 to the fourth. Hey, that's a nice cancellation there. I'm really just finding 3 to the third. 3 times 3 times 3. The answer should be 27. Okay, so kind of working our way through a sort of a factor tree situation, and we're going to come across more techniques to do this in more complex situations later on, how to simplify. But for the most part, this is what we're trying to do, undo the roots with powers. The next one, negative 64 to the 4/3 power. Well, the denominator, the 3 on that exponent, will make it smaller, so I've got the cubed root of negative 64, and then that's getting raised to the 4th power. Okay, well, let's see. Cubed root of negative 64 would be like negative 8 times 8, which would be like the cubed root of 4 times 2 times 2 times 4. Oh, 2 times 2 in the middle. Okay, I'm starting to see where this is headed now. I've got the cubed root of, let's call this negative 4 times negative 4 times negative 4, right? I'll still get to the same thing underneath that I had up above, but now I'm expressing it as something cubed underneath. I'll still create, this will still make a negative 64 underneath, but now I can call it the cubed root of negative 4 cubed, and then that to the 4th power. Remember, a negative number is totally fine underneath an odd radical. So we've rewritten it so that our cube root and cube cancel each other out. I'm taking negative 4 to the 4th power. Well, that's going to be like negative 4 times negative 4. That's a positive 16 times another negative 4 times negative 4. Another positive 16. Final answer should be 256. And we may have to do some scratch work, multiplication off to the side. If we know our perfect squares up to 20, then this should have been no problem whatsoever. And number 18, let's keep rolling. 16 to the negative 7/4. Okay, well that's the same as 1 over 16 to the positive 7/4. That's like 1 over, denominator makes it smaller, 4th root of 16 to the 7th power. So let's see, how can I break apart that 16 so I have something to the 4th underneath? Well, 16 is 4 times 4, and then 4 times 4, I can call that 2 times 2 times 2 times 2. Okay, so I've got the 4th root of 2 to the 4th, and I got my 4th root and 4th power underneath to cancel each other out. So really, that's like 1 divided by 2 to the 7th. And 2 to the 7th, it's a big one. It's 128. So I've got 1 over 128. And again, we may have some work to do off to the side by scratch. A good one to remember is that 2 to the 5th equals 32. So that way I know that it's pretty easy to work from there. 2 to the 5th equals 32 is the one that I remember. That way I know that 2 to the 6th, I would just multiply in another 2. Oops. I would multiply in another 2 and get to 64. 2 to the 4th, I would multiply in 1 less 2 and have 16. So if you remember this one, it's pretty helpful. It makes it somewhat easy to navigate those powers of 2 from there. But main story of this slide is getting to this point in each problem where we have our root and our power canceling each other out. All right, next example, evaluate using a calculator. We just need to know what to type in, and we need to be careful with things like negative signs and parentheses. So for number 26, if I have 1695 and I want the 7th root of that, I'm going to type in my 1695, and I'm going to raise it to the 1 divided by 7 power. Right? It's like 1695 to the first, and I'm taking the 7th root of that. First power, 7th root. So let's see what that gives us when we type that into the calculator. 1695 raised to the, and then in parentheses, I'm going to do 1 divided by 7. So my exponent is closed in parentheses. And I get 2.89. And that's just an approximate answer. I believe it says in the instructions to round to the nearest 100th place in our textbook. For number 32, here I've got -8, and I've got the 5th root of that to the 8th power. So in the calculator, I've got -8 caret, okay, the power is making it larger, and the root is making it smaller, so 8 divided by 5 is what goes in parentheses. So I'm also going to put the -8 in parentheses because I don't want it to leave that negative sign out in front of all the work. -8 raised to the 8 divided by 5 power, and I get 27.86 when we round. So there we go, how to use our calculator to type those in, and then, of course, rounding the answers. Some calculators may have, like if you look through the catalog, they may have a root key that you can type in the root and type in the powers and everything afterwards. I think typing them in as fraction exponents, rational exponents, is much, much faster. The last thing we're going to cover today is finding real solutions of an equation by taking the roots. So now we don't need to factor, we just need to solve. Okay, and solving without having to factor means we'll typically end up with only real solutions if possible. So for 36, man, I see a cube that I need to undo, but that 5 out front is kind of getting in the way. I need to divide that 5 out first. So I find that x cubed is equal to, I believe that's 216. And then how do we undo a cube? Well, we take the cube root of both sides. So my answer for x is the cube root of 216. In my calculator, I would type in 216 raised to the 1 divided by 3 power to make that happen. And we find that x equals 6. It comes out nice and clean. All right, and then number 40, here I've got a quantity to the 4th equaling 256. Well, I want to undo that 4th power so I can get to x. I undo a 4th power with a 4th root, so I find that x minus 5 is equal to the 4th root of 256. And I'll find that in my calculator by raising 256 to the 1/4 power. That's the quick way to type out a 4th root. And I find that x minus 5 is equal to 4. And now I just need to finish solving. So how do I finish solving? I add 5 to both sides. Welcome back to Algebra 1. X equals 9. And for either of these cases, if we ever had any doubt, we could plug our answer back in and see if the equation is true. So like for the first one, if I plug in a 6, is 5 times 6 cubed? I'd type that into my calculator and see if that equals 1080. Is that true or not? And let's just type that out really quick because I always want to be sure that we're certain of our answers. So 5 times 6 to the 3rd, it's 1080. Hey, we did that one right. Now let's try the next one. 9 minus 5. I got to do the work in parentheses first. Plugging in to check 9 minus 5, is that to the 4th equal to 256? So let's do the 9 minus 5. That would just be 4, and then raised to the 4th power. I hope I get 256, and I do. So both of these answers checked out. They made true statements when I plugged my answer back in. We know we did that work correctly. Okay, that does it for section 5.1. Here's a look at your assignment for this section.